Every year, banana jam moves through global food systems in large volumes, stored and distributed long before most people notice it exists. Most banana jam is not eaten directly. It is added to other foods, often without any further cooking or steps. Because the jam is added at this stage, any contamination present will reach the consumer unchanged. At this point, the manufacturing outcome is already fixed. Safety and shelf life were decided much earlier. Once shipped, problems cannot be corrected. Distribution only reveals the consequences of earlier decisions. Here, banana jam becomes invisible, embedded inside other foods, but still biologically active. This is where the process ends. Any failure in hygiene earlier is no longer hidden.
Banana jam begins in agricultural plantations, where fruit is grown for processing consistency rather than visual quality.
Ripeness determines sugar development. Uneven maturity creates chemical conditions that later hygiene control.
Harvest introduces the first irreversible risk. Microorganisms transferred here cannot be completely removed later. Gentle handling reduces tissue damage, slowing microbial growth before the factory process begins. Tools move between plants. Without cleaning, contamination spreads invisibly from harvest to harvest.
When fruit is stacked together, contamination concentrates. One compromised bunch can affect many.
From this point forward, time becomes critical. Delays allow contamination to grow beyond correction.
Arrival marks the boundary between open agriculture and controlled food manufacturing.
The receiving dock functions as a filtration point. Not all fruit moves forward.
Automation reduces handling. Fewer contact points mean fewer contamination pathways.
Inspectors look for damage, mold, or early fermentation. These signs cannot be corrected later. This is the last stage where contamination can be physically removed rather than controlled.
Once accepted, the fruit becomes part of a shared system. Isolation is no longer possible. From this point forward, hygiene control determines whether the product will ever be safe.
This is the first attempt to reduce contamination. Washing removes surface soil, but it cannot sterilize the fruit. Water removes visible contaminants, but microorganisms embedded in the peel remain unaffected. After washing, the fruit appears clean. Biologically, it is not. Sorting reduces variability. Uneven fruit creates uneven microbial behavior during later processing. Peeling is irreversible. Once the flesh is exposed, contamination can no longer be washed away. The protective barrier is gone. Any contamination introduced now spreads instantly. From this moment on, hygiene depends entirely on equipment, not washing. Pulping marks a structural shift. Individual fruits are about to become a single shared mass. Once cut, the fruit can no longer be separated. Contamination becomes impossible to isolate. At this stage, any microorganisms present spread instantly through the entire batch. Oxygen control slows browning and microbial activity, but it cannot reverse contamination already present. The product is now one material. From here on, every decision affects the entire batch. Once enclosed, the pulp cannot be cleaned again. Hygiene now depends entirely on system integrity. From this point forward, contamination can only be controlled, never removed. Sugar is not added for sweetness alone. It is a primary preservation tool. By binding available water, sugar limits microbial survival. The amount must be exact. Mixing ensures every portion of the batch shares the same microbial resistance. If sugar is unevenly distributed,
Isolated zones can still support microbial growth.
Once mixed, the batch becomes chemically uniform. Errors here cannot be separated later. Sensors confirm conditions, but they do not fix mistakes. The process must already be correct. The batch now moves forward as one system. All contamination control depends on what comes next.
This vessel marks the most critical hygiene intervention. Heat is now used to suppress microbial survival.
Temperature must remain within a narrow range. Too low allows survival. Too high. Circulation ensures every part of the batch experiences the same microbial reduction. As water is removed, the jam becomes less hospitable to microbial growth.
Reducing moisture limits microbial activity, but only if heat exposure is sufficient and uniform. This texture change signals preservation. If achieved incorrectly, it cannot be corrected later. Once cooking ends, reheating is no longer an option. Contamination control becomes fragile.
After cooking, the jam must be moved. Heat protection is over, but exposure risk begins.
Every joint is a vulnerability. If seals fail here, contamination enters permanently. Valves control movement, not safety. Once opened, they cannot disinfect the product. Pumps move product efficiently, but they also spread contamination instantly if present. At this stage, hygiene exists only if the system remains sealed.
The jam enters stabilization without another kill step available. This window is unforgiving. Contamination introduced here cannot be removed later.
After cooking, the jam must be chemically stabilized. Heat alone is not enough for long-term safety.
Acidity creates an environment where most microorganisms cannot survive.
Once acidity is adjusted, it cannot be removed without destroying the product. Homogenization ensures acidity reaches every portion of the batch.
This is the final opportunity to create uniform safety conditions.
Instruments confirm stability. They do not correct mistakes.
The product is now chemically locked. Errors beyond this point cannot be reversed.
Testing begins with sampling. This portion must accurately represent the entire batch.
If the sample is compromised, the test result becomes meaningless. Laboratory handling introduces its own risks. Clean technique is essential.
pH confirms whether microbial growth is chemically suppressed. These tests do not remove contamination. They only reveal whether it exists. Test results determine whether the batch can continue or must be destroyed.
Only now is the product allowed to move forward.
Hot filling relies on residual heat to suppress contamination during packaging.
Containers must be sterile. Any contamination here is immediately sealed inside.
Once filled, the product cannot be cleaned again.
Time between filling and sealing is kept extremely short.
The seal determines shelf life. A failed seal cannot be repaired. From this point forward, safety depends entirely on seal integrity.
Cooling stabilizes the seal and locks the product into its final state.
Once packaged, the jam enters storage. The product is sealed, but not immune to damage.
High sugar and acidity allow ambient storage, but temperature abuse can still cause failure.
Handling no longer affects hygiene directly, but physical damage can break seals. Once shipped, The factory no longer controls conditions. Distribution time varies from days to months, depending on destination.
The product remains safe only if seals and storage conditions remain intact. From here, banana jam becomes an ingredient rather than a product.
Opening the container ends factory protection. From this point on, hygiene depends on the user.
In many products, the jam is not reheated. Any contamination present is carried forward. This is how most banana jam is consumed, embedded inside another food. By the time it reaches shelves, all safety decisions are already locked in.
The consumer inherits the results of every step before this moment.
Nothing more will happen to this product. It will not be corrected or improved.
This is where the manufacturing process truly ends.